Everything we do, from something as simple as lifting a coffee cup to the incredible precision of open heart surgery, it all hinges on this incredibly delicate system of control we have over our own muscles. We can start a movement, stop it, or hold perfectly still, all on command. But what happens when we want to, or more importantly, need to, turn that whole system off? Or maybe even jam it on? Believe it or not, for centuries we've been hacking this exact system. It's a journey that's taken us from poison darts in the jungle that paralyze prey, all the way to the sophisticated drugs that make modern surgery even possible. So how does it all work? How do we hijack our body's most fundamental command pathway? Let's dive in. Okay, so before we get into all the cool hacks, we first have to understand the system we're actually hacking. And really, it all comes down to this one tiny, elegant, and absolutely critical checkpoint in our nervous system. This is it. This is the spot. It's called the neuromuscular junction, or NMJ for short. The best way to think of it is as the ultimate on switch for your muscles. It's this microscopic gap where the very end of a nerve cell comes right up to a muscle fiber. Every single voluntary thing you do, blinking, walking, running, you name it, that command has to pass through this checkpoint. So how does this switch actually get flipped? Well, it happens in a flash in basically 5 key steps. First, an electrical signal zips down the nerve. That signal's arrival triggers the release of a chemical messenger called acetylcholine. We'll just call it ACH. That ACH shoots across the gap and latches onto receptors on the muscle. That connection is what activates the muscle and makes it contract. And then, just as quickly, an enzyme swoops in to clean up all the leftover ACH. This resets the switch, getting it ready for the very next command. It's elegant, it's precise, and it is incredibly fast. All right, now for the really fun part. What if we want to deliberately flip that switch to the off position? This is where pharmacology gets super clever, creating a state of controlled paralysis that, as it turns out, is absolutely essential for modern medicine. And there are really 2 fundamental ways you can pull this off. You can either stop the signal, that's the acetylcholine, from ever being sent out from the nerve in the first place, or you can just let it get sent, but physically block it from ever being received by the muscle. Let's take a look at that first one. So meet botulinum toxin. You've probably heard of it. It is one of the most potent poisons known to science, and it works before the signal even crosses the gap. It literally stops the nerve from releasing its payload of acetylcholine. No messenger means no message. The command to contract never even leaves the station. And when this happens by accident, well, the results can be absolutely devastating. Back in 1922, at the Lochmaree Hotel in Scotland, 8 guests ate some sandwiches that were contaminated with this exact toxin. Every single one of them died from a progressive paralysis because eventually even the muscles that control our breathing were switched off. It's a really stark reminder of this toxin's raw power. But here's the truly wild part. By taking that exact same power and harnessing it in microscopic, hyper-controlled doses, we've turned this deadly poison into a revolutionary medical tool. Today, we inject it, you know it as Botox, to do everything from smoothing wrinkles and stopping muscle spasms to treating overactive bladders and even correcting crossed eyes. It is the perfect example of how deeply understanding a system gives us the power to control it. Now let's jump to that second off-switch hack, blocking the signal after it's been sent. And this story starts deep in the Amazon with a plant used to create a poison called curare for hunting darts. But its incredible journey has ended up right here in the modern operating room, where its chemical descendants are now totally crucial for keeping patients safe. Modern drugs, like rocuronium, are built on this very principle. They're what we call competitive antagonists. Honestly, the easiest way to think about it is like a game of musical chairs. The drug molecules get to the acetylcholine receptors first, and they just sit there, taking up all the spots. So when the real ACH shows up, there's nowhere for it to bind. The signal gets sent, but it has nowhere to land. This creates a temporary, perfectly controlled paralysis, a muscle relaxation that's essential for surgery. Okay, so turning the switch off makes sense. But what about a totally different, much more paradoxical kind of hack? What if I told you that you could cause paralysis by jamming the switch permanently on? So let's break this down, because it's a little counterintuitive. When you block the switch, you get a straightforward limp paralysis. But when you jam it on, you first get this burst of uncontrolled muscle twitching, and then you get paralysis. So why does that happen? Because the receptor is held on for so long without any break that it basically just burns out. It becomes desensitized and just stops responding, so it can't reset for the next real signal. The classic drug that pulls this off is called suxamethonium. It's what's known as an agonist, which just means it's a perfect mimic for acetylcholine. It binds to the receptor and activates it, no problem. But here's the trick. It doesn't get cleared away by that cleanup enzyme. It just sits there on the receptor, firing it over and over and over again, causing that constant activation that, weirdly enough, leads to paralysis. Now, this is where things get really interesting and, frankly, a little bit terrifying. For most people, suxamethonium's effect only lasts for a few minutes, but it turns out about 1 in every 3,500 people has a genetic variant that means their body can't break down this drug properly. So for them, a paralysis that should last maybe 4 or 5 minutes could end up lasting for hours. But we can actually push this concept one step further into some truly dangerous territory. What if instead of mimicking the signal, you just disabled the off switch entirely? That's what a class of chemicals called irreversible anticholinesterases do. And you find these in things like military nerve gases and some very powerful pesticides. Their mechanism is just brutal. They permanently knock out that cleanup enzyme, acetylcholinesterase. That means every last bit of acetylcholine your body releases just builds up and up and up in that little gap, with absolutely nothing to clear it away. The result is this catastrophic system-wide overstimulation. And because the enzyme is permanently broken, the only way to recover is for your body to slowly build brand new enzyme molecules from scratch, a process that can take weeks. But for every hack, science tries to find a counter-hack. For every poison, there's a potential antidote. We haven't just figured out how to turn the switch on and off, we've also figured out how to restore normal function when things go wrong. Let's go back to surgery for a second. How do we wake the muscles back up? Well, the old way, with a drug like neostigmine, is basically a brute force approach. It temporarily blocks the cleanup enzyme, which floods the junction with so much of your own natural ACH that it can just overwhelm and outcompete the blocking drug. But the modern way, with a drug like sugammadex, is so much more elegant. It's a designer molecule that's shaped to perfectly find, trap, and literally hug the blocker drug, physically yanking it out of the system. And what about that ultimate jam, the nerve agent poisoning? Well, there's a counterhack for that too. There's a class of drugs called reactivators, like pralidoxime, that can perform what is basically a molecular rescue mission. It's designed to find that disabled enzyme, latch onto the poison that's stuck to it, and essentially just pry it off. This frees the enzyme, allows it to start working again, and brings that critical master switch back online. When you think about it, from poison darts to Botox to life-saving antidotes, the story of the neuromuscular junction is really a story about control. It shows how, by understanding a biological switch at its most fundamental level, we've gained this incredible power to turn it on, turn it off, and even fix it when it's broken. It really makes you wonder, as our power to hack our own biology keeps growing, what's the next switch we're going to learn how to control?